Okay, in this video we're going to talk about Euler's method for approximate solutions to ordinary differential equations. And you might say that this is the benchmark application of numerical analysis. This is one of the earliest applications of numerical methods, and it remains one of the most important applications of numerical methods. Euler's method is the very simplest method for approximating solutions to ordinary differential equations. It's still used. It dates back to Euler, who was probably 300 years ago, and it's still the basis for more sophisticated methods. So in this short video, I'm going to introduce the rationale behind Euler's method, and then in the next video, we'll put it on a spreadsheet. Okay? So Euler's method is a solution for solving ordinary differential equations. Mathematicians first became interested in these things when they were studying equations of motion, particularly equations of motion of the planets. That was very interesting to Newton and others. So you can use Euler's method when the differential equation has this form: the derivative of y as a function of x is equal to some given function of x and y, where y when x equals 0 is a specified value. We have some examples here. If you have a differential equation like this, dy dx plus 2y equals 1.3 e to the minus x, that doesn't quite look like this form, but you can rewrite it so that the derivative is by itself on the left-hand side. And in this case, we get dy dx equals 1.3 times e to the minus x minus 2y. And the initial condition, y of 0 equals 5, is furnished as well. So this has exactly the form we need in order to use Euler's method. And they show various other applications of this. They have this more complicated differential equation, which can still be put in Euler's form by putting the dy dx by itself on the left-hand side. In this case, the function f of xy is everything that's on the right-hand side. Now, the idea behind Euler's method is not so complicated. We are given the value of y at a particular point. When when x is equal to 0, y is equal to 5. So we know one point of the solution, and that's this point represented here. In general, we call that x0, y0. Now we want to know what the solution will be for future values of x, for larger values of x. So let's, in keeping with the philosophy of calculus, let's try to find the solution for a value of x that is slightly bigger than x0. In our case, x0 is equal to 0. Why don't I just go ahead and write that in? Here. Okay, so this is the initial point. All right, so we're taking h as something to be small. And what that means is that the tangent line to the solution curve is quite close to the secant line of the solution curve. We saw this before when we were finding roots, that we would approximate a tangent line with a secant line. So when h is small, the tangent line is approximately equal to the secant line. And that's the whole idea behind Euler's method. What that means is their slopes should be approximately equal. Their slope should be approximately equal. All right. Well, what is the slope of the tangent line? Well, that's dy dx at x is equal to x0. What is the slope of the secant line? Well, we can compute it as, if that's the point here, the true value of the solution here would be x1, y1. Okay, so we can go down where he writes all of this out. This is equal to the slope of the secant line. All right, if we have the 2 points x0, y0, and x1, y1, this is the slope of the line that joins those two. Now, what are we going to compare this to? Well, we're going to compare it to the slope of the tangent line, which is actually equal to f of x0, y0. Now, why is that true? Since we have dy dx is equal to f of xy, that means that this value here is equal to the slope of the tangent line, right? That's just what the derivative means. It's the slope of the tangent line. So the slope of the tangent line at x0, y0 is equal to dy dx, and that's equal to f of x0, f of y0. Okay. So what equation do we have here? We have y1 minus y0 over x1 minus x0 equals f of x0, y0. Let me just write it up here. y1 minus y0 over x1 minus x0 is equal to f of x0, y0. Okay. All we have to do is rearrange this and solve for y1, and we get this result down here. All right. What did we do? We multiplied both sides by x1 minus x0, and then we added y0 to both sides. Okay. So we have this equation for y1 in terms of y0, which we know, f of x0, y0, which we know, and x1 minus x0. Well, what is x1 minus x0? Go up to this picture here. x1 was the value of x that's slightly bigger than x0, and the difference between these two was equal to the step size h. All right, so that's exactly what we have here. We can replace this x1 minus x0 with h, and here we have our Euler's equation. Okay. This will give me y at the next point in terms of my values of x and y at my initial point, and the step size h, and the known function f of xy. But why stop there? Once I've gotten to x1, I can do the very same thing, right? When I'm at xi, this point is xi, yi. Think of I equal 1 for the moment. Okay. I want to find the solution at a value of x slightly larger. That's going to be my xi plus 1. The difference between these two x's is h, same as in our original condition. And we still want to equate the slope of the tangent line is approximately equal to the slope of the secant line. So this is the slope of this. This is the secant line right here, and the slope here is going to be yi minus yi plus 1 minus yi over xi plus 1 minus xi. And then here's the tangent line. It didn't work out somehow. The tangent line should be like this. It should be something like that. And the slope of this is equal to dy dx evaluated at the point x equal xi. And that's equal to f of xi yi. Okay. So I set this slope of the tangent line, of the secant line rather, equal to the slope of the tangent line. Slope of the secant line equals the slope of tangent line. And I get a very similar equation to here, except instead of y0 and y1, I have yi and yi plus 1. So my general formula that I'm going to implement in my spreadsheet is this simple little formula here. The next value of y is equal to the previous value of y plus known function of f times h. And h is a fixed number that I know the value. So that's what we're going to do in our spreadsheet, and we'll see you in the next video.